Okay, so in this numerical example, write the differential equation of the motion for the system shown in this figure here, and determine the natural frequency of the damped oscillation and the critically damped coefficient. So obviously you are given this diagram here. So mass is attached here. A damper is attached here to the mass directly under the mass, and under the mass, and the K is a spring is attached here with a constant K, and the constant here is C, and the distances are given from here to here it's A, and from here to here it's B. So write the differential equation. So what you need to calculate: A, uh, differential equation, and determine the natural frequency of the damped oscillation, and B that you need to calculate is omega D, and the critically damped coefficient, and C is you need to calculate CC. Okay, so to draw the first thing is, if you want to derive the equation, the differential equation here, so you will need to draw the free body diagram in this case. So to draw the free body diagram, so we know that we give this system a slight angular deformation here. We will solve this system in the angular coordinate system here. If we give it a smaller angular displacement theta in this direction, so then we know that the velocity and acceleration, which is theta dot and theta double dot, are positive in this direction here. Now the mass is attached here, so mass is attached here, and if the body will move in the downward direction, so the Cx dot will be in this direction here, and similarly the Kx will be in this direction here. Okay, so these are all the forces which act on this system here. So now what we need to do is that we need to represent this x dot in term of theta dot and x in term of theta. So we know that okay, so in this case, uh, because as we did in the previous case, that because this angle is very very small, so then x here, which is this distance here, or this distance here. So as you can see that this x is just equal to, so for example in this position here, so if you call this x1 and call this x2 here, so this x1 and this call this x2, so we will call this x1 and this x2. So this x1, which is this distance here, is just a sine sine theta, and x2 is just equal to b sine theta. And now because the angle is very very small, so we can say that sine theta is equal to 1, and this is equal to 1. So x1 is equal to a, sorry, sine theta is equal to theta. If the angle is very very small, so this will become a theta, and this will become b theta. This means that we can replace this the cx dot by c a, and if you want to write x2 dot, so which will become just b theta dot, or or a Okay, so x1, okay, yeah, so x1 is equal to a theta. So x1 dot become equal to a theta dot. This become equal to a theta dot, and then kx2 will become equal to kb theta. So we just replace these by these things here. Okay, so now these are now the forces in terms of theta. So to write the equation of motion here, we will say that summation of all the moments uh, about O, which is this point here, is equal to I naught, which is the moment of inertia about O, and theta double dot, which is the angular acceleration here. And the angular acceleration is positive in this direction here. So this means that the moment which this force and this force will produce will be in the opposite direction. So what will happen is that the force here is CA theta here. So the first force is CA theta and the minus sign because it's opposite to the theta double dot. And then you need to multiply with the moment arm here. So the moment arm in this case is this distance here from here to here. And we know that this distance here is a cos theta. And so this distance is a cos theta. And this distance from here to here is b cos theta. And now because angle is very, very small, so then cos theta is equal to 1. Then this is b and this is a. So you just need to multiply this force with a. And in this case, it's kb theta, so you will just multiply with b and equal to I naught theta double dot here. So you get this equation here. Now because it's a concentrated mass, so even we can write the equation for I naught, which is m a double dot, sorry, m a square. Ma square is the moment of inertia here. So if we just put all these values and just simplify equation, so it will become ma square plus c a square, and this will be theta double dot c a square theta, and minus kb square theta equals 0. This is the equation of motion, that is what we need to calculate. So ma square theta double dot uh, and then ca square theta and then plus kb square theta equal to 0. So this is the equation of motion. Now the second thing is we need to calculate omega d and tc. So for this case, then we will need to simplify this equation here. So now we can simplify this equation. So if you just write this equation is theta double dot. So if you just divide by ma square, so is equal plus ca square divided by ma square plus kb square ma square theta dot, and this theta equals 0. Can cancel a with a. So theta double dot plus and this will become equal to c divided by m theta dot and plus k divided by m b square a square theta equals 0. So now in this equation, if you compare this equation with our original equation that we derived for a simple case, which was x double dot. So comparing, if you compare this equation, so comparing with x double dot plus 2 zeta omega n x dot plus omega n square equals 0. If you just compare with this equation here, so you just so here you have theta double dot and you have x double dot. Here you have theta dot, here you have x dot, and here you have theta, and you have also uh, x here. So if you compare this equation here, so what you will get is that x double dot, that this term here, that 2 zeta omega n is equal to this this thing here. So we can say that 2 zeta omega n is equal to c divided by m. So this term become equal to this term here. So from here you can calculate zeta, which will become equal to c divided by 2 zeta m omega n. So then this is the value of the zeta here. And we can further simplify this by putting the value of the omega n here. So it will become equal to 2 and 2m. So yeah, so 2 c divided by 2m omega n. So it become equal to 2m, and omega n, in this case we can calculate omega n here. Okay, so omega n, but omega n here in this case, if you compare these two values together, so omega n become equal to b by a and k by m under the root. This is omega n, so we will just need to take the root of this thing here. This become omega n here. So if you just put omega n in this equation here, so zeta will become equal to c to m and b by a k by m under the root. So in this case, you can simplify this equation here, so which become equal to AC and 2B and Km under the root. So you just simplify this equation and it become like this. Now, if you want to calculate this CC here, so CC, which is part C of this problem, so CC will become equal to when this zeta is equal to 1. So then A, and then the C becomes CC and 2B Km under the root. So this will give you CC here. So CC will become equal to 2B Km divided by A. So this is the value of the CC here. Now finally we need to calculate this omega d, and we know that omega d is equal to omega n 1 minus zeta square. So if you just put the value of omega n, which is this value here, so b divided by a and k by m, and 1 minus zeta square. So zeta in this case was this value here. So the zeta is AC. So it become AC to be Km under the root square. If you just simplify this equation here, so what you will get is Km B square B by A whole square minus C divided by 2M whole square under the root. This is the value of the omega d, which is your part B here.